The radial component of distortion plays a crucial role here. It measures the deviation of points from the center of focus, providing valuable information for dynamically adjusting the captured image's focal point. Instead of relying on complex pre-calculated models, we aim to simplify the process by focusing on basic, geometrically sound principles. The goal is to identify how basic, concrete factors interact within the environment, then use that understanding to develop a dynamic system for real-time distortion correction. In our approach, we take the core concept of geometry and apply it to our problem. While mathematics and advanced modeling are often used to simplify and abstract the issue, we believe that grounding the solution in geometry can lead to a more intuitive and adaptable system. The idea is to avoid overly complex equations and instead focus on the direct relationships between geometric elements. This also ties into the way humans tend to abstract and complicate things, but here, we focus on practical, well-studied principles, like the behavior of parabolas in geometry, to guide our distortion correction efforts. The key here is adapting to dynamic environments. Rather than applying a generic, predetermined lens distortion correction, our approach involves working backward. We measure distortions empirically by comparing the observed distorted points, like the positions of dots on a matrix, with their known undistorted positions. From this comparison, we derive specific equations for each lens and scene configuration. This reverse engineering approach allows us to calculate distortion equations that are tailored to the unique setup in real time. One major advantage of this system is its adaptability. As distortions are measured and mapped, equations are derived to correct for them. The process involves fitting dynamic equations, like R equals 1 plus A1 R2 plus A2 R4 plus A3 R6, where A1, A2, A3 are computed based on the observed data. These coefficients replace static distortion coefficients, allowing the model to adapt in real time to the specific lens and environmental conditions. This approach is ideal for environments where pre-calibrated distortion models may not be available or effective. To further visualize this method, think of a rubber sheet with a dot matrix drawn on it. If the sheet is stretched, the positions of the dots will shift. By dynamically measuring how far the dots have moved from their ideal positions, we can reverse the stretch and reconstruct the original shape of the sheet. In the case of lens distortion, this process is applied to correct the perceived geometry of the scene, restoring the accurate structure of the observed objects or human bodies. This applies not only to bodies but to any object experiencing distortion, such as those with concave or diverging effects, which can be corrected by repositioning the edges to their correct spots. One challenge with this approach is ensuring that the data used for these calculations is accurate and consistent. A fixed backdrop with known dimensions, such as a checkerboard or matrix of dots, is used to capture the distorted image. Since the distortions we are dealing with are typically small, it's important that this backdrop is comprehensive and precisely documented in the software. Additionally, real-time analysis must be capable of identifying distortions and making corrections without overwhelming the system's resources. The next phase of development involves programming the software to automatically correct distortions based on predefined terms. The goal is to translate the distorted projection back into the ideal projection, considering the tolerances and adjustments necessary to achieve the desired result. This process will likely require several phases of real-time data processing, which we are still working to perfect. The use of machine learning could help reduce the amount of manual calculation needed, though challenges remain in managing the complexity of human bodies, which are highly irregular and difficult to model universally. Another important aspect of this method is its ability to account for various factors such as lighting, shadows, and camera angles. By incorporating these elements into the correction process, we can make the system more adaptable to different environments. If the camera is positioned too high or too low, these variations in view can also be corrected, ensuring that the consumer experience remains as simple and intuitive as possible. In conclusion, our approach leverages geometry and simple, well-established principles to create an adaptive, real-time solution for lens distortion correction. By working backward and measuring distortions empirically, we generate dynamic equations tailored to the specific lens and scene configuration, which can be used to reverse distortions and restore accurate geometry. While this method is still in development, we believe it offers a more flexible, precise solution than traditional, static distortion correction methods. The next steps involve refining the system to handle various real-world factors, such as lighting and camera angles, and ensuring that the software remains efficient and effective in processing real-time data. The key concept at play here is leveraging quadratic functions, specifically parabolas, to map pixels from a distorted image to a corrected one. The core idea revolves around applying a transformation, often referred to as parabolic warping, that straightens out bending and distortion by adjusting pixel positions along curves defined by a parabolic equation. This method is especially useful when dealing with images captured by consumer cameras, which can introduce distortions such as radial, barrel, or pincushion effects. In the initial development phase, parabolic warping was central to the approach. This involved using quadratic equations to correct distortions. The equations mapped distorted pixel locations back to their true positions on a corrected image. While effective in achieving precision, this method required a robust mathematical framework and computational overhead. For real-time applications, such as analyzing images from consumer devices, these complexities posed challenges. To simplify the process, we developed an alternative approach that retained the essence of parabolic warping but minimized reliance on direct quadratic equations. Instead, the revised method focuses on a foundational setup, a meticulously designed backdrop that provides the necessary reference data for distortion correction. The backdrop is critical in this system, serving as the baseline for both spatial alignment and distortion correction. Designed with precision, it typically features a black and white checkerboard pattern combined with a red dot matrix. This color scheme and pattern design are intentional, as contrasting colors like black, white, and red are easily detected by cameras and provide high visibility. The checkerboard pattern offers a clear geometric grid for calibration and spatial alignment. Alternating colors help the system interpret image geometry and adjust for distortions. Red dots act as data nodes or anchor points for pattern recognition algorithms, creating a framework that interacts with the user's body to provide depth and spatial data. By integrating these features, the backdrop not only facilitates distortion correction but also eliminates reliance on the subject's physical characteristics, such as skin tone or clothing. A significant consideration in the design is preserving user privacy. The system does not store actual images or videos of the users, particularly given that they might be scantily dressed for body measurements. Instead, the system processes data in real time, extracting only essential metadata in the form of lines, dots, and spatial relationships. This ensures that no sensitive visual data is retained, addressing potential privacy concerns and making the product more user-friendly. However, this approach introduces challenges in consumer guidance. Users must be properly instructed on where to stand and how to position themselves without feeling overwhelmed. Effective customer support plays a crucial role here, ensuring that the process is intuitive and approachable. Distortion correction hinges on understanding the type of distortion, radial, barrel, or pincushion, and applying the appropriate model. Without a reliable backdrop, it becomes nearly impossible to determine the exact origin and nature of distortion. The backdrop provides a fixed reference against which distortions can be measured and corrected. Inverse mapping is key to this process. Rather than mapping from the corrected image back to the distorted one, the system maps distorted pixels to their correct positions on the ideal image. This ensures that the corrected image retains its integrity, as the algorithm accounts for distortions based on the known parameters of the backdrop. The data nodes on the backdrop, such as the red dots, serve as input variables for algorithms designed to interpret spatial relationships. These algorithms analyze how the user's body interacts with the backdrop, using the detected distortions to calculate corrections. The resulting math is dynamically performed by the software in real time, leveraging the backdrop's known properties to make precise adjustments. One challenge in real-time processing is ensuring efficiency. High computational loads from parabolic calculations or detailed distortion models can slow down performance, which is unacceptable for consumer-facing applications. Streamlining the algorithm while maintaining accuracy is a critical part of the development process. The use of contrasting colors and patterns on the backdrop also enables the exploration of advanced imaging techniques. By leveraging inverted color schemes or negative space analysis, the system can highlight details not easily visible in a standard view. These techniques enhance contrast and enable the software to distinguish between regions or elements more effectively. For example, reverse contrast features can reveal additional details, aiding object detection and tracking. This dynamic interplay between high contrast elements, checkerboard patterns, and red dot matrices allows for layer analysis, improving depth perception and clarity. These elements act as markers for calibration and feature extraction, ensuring precise spatial analysis. Parabolic warping remains a potential tool for refining these processes, particularly in applications requiring high precision. For instance, when zooming into a magnified image, parabolic warping could help trace fine edges or adjust for minute distortions. While the initial implementation minimizes the use of quadratic equations, future iterations may reintroduce them for enhanced precision when needed. Additionally, the integration of parametric modeling, discussed earlier in the series, offers further opportunities for refinement. Parametric modeling allows for dynamic adjustments based on user-specific data, potentially improving the accuracy of body measurements and distortion corrections. We can utilize interpolation techniques such as bilinear and bicubic interpolation, or even extrapolation when necessary, to address missing data points in an image. These methods are foundational for refining image quality and filling in gaps effectively. While interpolation is useful, we can also explore distance-based arc approximations for cases where more intelligent pixel predictions are required. However, this technique is reserved for extreme scenarios, such as when a customer is using a very low-quality camera. The goal is to ensure the system remains accessible to as many users as possible, including individuals with disabilities, while also maximizing customer satisfaction and usability. For users unable to stand, we plan to implement features that accommodate their needs. Distance-based arc approximations work by estimating missing pixel values based on their proximity to known points within a defined geometric structure. In our system, these known points form a dot matrix embedded within a checkerboard pattern. The checkerboard provides a geometric reference that enables precise detection of distortions in the image. Using this approach, we can trace a person's body geometry by referencing data nodes created by the grid intersections within the checkerboard. The idea of using a checkerboard pattern for calibration is well established in computer vision, as it provides a reliable grid for determining distortion parameters. To enhance precision, we propose incorporating parabola overlays onto the checkerboard. These overlays help identify subtle distortions, such as barrel or pincushion distortion, which can warp straight lines into curves. Given that the human body is inherently curved, modeling these distortions accurately is crucial for achieving high precision. The checkerboard pattern lays the geometric foundation for detecting distortions, while the parabola overlays allow for fine-tuned adjustments to account for lens curvature effects. In practice, this system employs inverse mapping techniques, checkerboard calibration, and real-time adjustments to correct distortions dynamically. For example, if a user moves or shifts their posture, the system can adapt on the fly to maintain accuracy. Although optimal camera angles are encouraged, the system is designed to function under suboptimal conditions to ensure ease of use. Customers shouldn't need to position their cameras perfectly or follow overly rigid guidelines. The system should handle as much complexity as possible. This approach minimizes friction for users, making the solution accessible and user-friendly. Lighting conditions are another critical factor. While optimal lighting improves results, the system can infer key information even under poor lighting conditions by leveraging color contrast. In extreme cases where lighting or camera quality severely impacts the image, a prompt can guide the user to adjust their setup. However, this should be an exception rather than the rule. The system's robustness should ensure minimal manual intervention, reducing frustration and increasing adoption rates. To further enhance precision, we suggest using a checkerboard pattern with a high density of grid points. The more grid points available, the more accurately the system can model distortions. Incorporating a scale factor into the checkerboard pattern, such as inches or centimeters marked alongside the grid, allows the system to map pixel data to real-world dimensions. This calibration step is critical for translating digital measurements into physical scale. Since it is unrealistic to capture all pixels perfectly, the dot matrix acts as a pseudopixel framework. These pseudopixels are designed to be as small and closely spaced as possible while remaining visually distinguishable, allowing the system to approximate missing data effectively. In summary, the system leverages a combination of interpolation, inverse mapping, checkerboard calibration, and parabola overlays to address image distortions and missing data. By incorporating features that accommodate various camera qualities, lighting conditions, and user needs, the solution aims to provide an accessible, high-precision tool for a wide range of customers, including those with disabilities. The checkerboard and dot matrix serve as the backbone of this system, enabling robust calibration and real-world dimensional mapping, while intelligent algorithms ensure minimal user effort and maximum usability. In the digital age, where software applications are expected to be adaptable and intuitive, understanding and leveraging pixel dimensions, screen resolution, and physical screen size has become fundamental for developers. This essay explores these concepts in detail, discusses methods to retrieve such information programmatically across various platforms, highlights associated challenges, and offers practical solutions for implementation. A pixel, short for picture element, is the smallest unit of a digital image that can be displayed and controlled on a screen. Each pixel represents a single point in an image, composed of 3 subpixels, red, green, and blue, that combine to display colors. The resolution of a screen is defined as the number of pixels arranged horizontally and vertically, expressed in terms like 1920 by 1080, Full HD, where 1920 pixels span the width and 1080 pixels span the height. The resolution is a critical parameter for developers as it determines the clarity and detail that can be displayed on a device. However, resolution alone does not provide a complete picture of the screen's physical attributes. To bridge this gap, developers often consider the pixel density, measured in dots per inch, DPI, or pixels per inch, PPI. Pixel density correlates resolution with the physical dimensions of the screen, influencing the perceived sharpness of images and text. Retrieving a device's screen resolution is a straightforward process and is supported across most platforms, including web, desktop, and mobile environments. In web development, JavaScript provides a convenient way to access screen resolution through the window.screen object. This method fetches the device's screen resolution in pixels, offering a quick solution for responsive designs and user interface adjustments. On desktop platforms, APIs and libraries facilitate resolution retrieval. Windows, developers can use the getSystemMetrics function from the Windows API. For instance, Python provides an interface through types. Linux and macOS, utilities like Xrand and libraries such as Quartz allow developers to query resolution data. Mobile devices expose resolution information through their respective SDKs. Android, the displayMetrics class can be used to obtain screen width and height in pixels. iOS, developers can use the UIScreen class to access similar information. These programmatic methods ensure that applications dynamically adjust to different devices, enhancing user experience. While resolution is easily accessible, retrieving the physical screen size is more complex. The physical dimensions, measured in inches or centimeters, depend on the screen's pixel density. This information is critical for applications requiring precise spatial calculations, such as augmented reality, computer vision, or graphics-intensive tasks. Browsers typically do not provide direct access to physical screen size due to privacy concerns. Developers can approximate it using the screen resolution and an assumed or detected pixel density. This method provides a rough estimate, sufficient for most user-facing applications. On desktops, physical screen size can sometimes be retrieved from the Extended Display Identification Data, EDID, which contains manufacturer-provided information about the monitor. Windows, use getDeviceCaps or third-party libraries to parse EDID data. Linux, tools like xtpinfo or Xrandr can provide physical dimensions. macOS, the Quartz framework includes methods to infer screen size. Mobile platforms often provide more accurate physical screen dimensions. Android, developers can divide pixel dimensions by DPI values, e.g., metrics.xp and metrics.idp. iOS, the UI screen scale factor can be used to derive real-world dimensions. Despite the availability of APIs and methods to retrieve resolution and screen size, several challenges remain. 1. Privacy and security limitations. Web browsers restrict access to sensitive device information to protect user privacy. 2. Dynamic multi-monitor setups. Users with multiple monitors may have screens of varying resolutions and physical dimensions, complicating application adjustments. 3. Non-standard devices. Older or niche devices may have atypical screen properties, making assumptions about resolution or density unreliable. 4. User-provided data. When physical dimensions cannot be retrieved programmatically, relying on user input can introduce inaccuracies. To address these challenges, developers can implement a combination of strategies. 1. Request user input. During application setup, users can be prompted to enter their device's screen size, which the software can store and reference. 2. Device databases. Leverage databases of known device specifications to infer screen dimensions based on resolution and user agent strings. 3. Standard assumptions. For general use cases, developers can assume standard sizes for common devices, e.g., laptops, smartphones, and monitors. 4. Adaptive designs. Build applications that adapt dynamically to varying screen properties, reducing dependency on precise dimensions. The interplay between pixels, resolution, and screen size is crucial for designing adaptable and user-friendly software. While retrieving screen resolution is relatively easy, determining physical screen size introduces additional complexity. By leveraging platform-specific APIs, estimating pixel density, and implementing adaptive design principles, developers can overcome challenges and deliver software that works seamlessly across a wide range of devices. As technology evolves, so too will the tools and techniques available, making it increasingly feasible to create precision-driven applications for diverse user environments. The goal of this project is to create a system capable of capturing precise 2D body data without requiring highly detailed pixel information. Instead of relying on high-resolution images or color data, the approach focuses on obtaining an accurate outline of the body and essential measurements. This system eliminates the need to process colors, textures, or even the individual pixels of the subject's body, which allows us to prioritize privacy and ease of use. One of the core design principles is ensuring user comfort and privacy. For instance, the software interface can be developed so that users don't see themselves directly in the viewfinder or capture area. Instead, their body is represented as a simple, shadow-like figure or a black silhouette. This feature addresses potential discomfort or anxiety, particularly for individuals with body image concerns, such as body dysmorphia. By obscuring the user's physical form, the system minimizes exposure and provides a safer, more comfortable experience. Another key feature is that the system collects no personally identifying or unnecessary data. Users can trust the system to focus solely on extracting geometric outlines and essential body measurements. This data minimization approach aligns with modern privacy standards and ensures that consumers feel secure while using the product. The design is rooted in creating a system that even the designers would feel comfortable using, something that inspires trust and confidence. This is especially important for a diverse user base, including individuals who might otherwise avoid such technology due to personal concerns. The technology employs a combination of matrix modeling and dot mapping. A grid-like checkerboard pattern is projected or used as a backdrop to aid in body mapping. Each square within the checkerboard grid functions as a collection of points in a 2D plane. By fitting these points to a parabolic model, the system can approximate the lens's distortion and create a reliable mathematical model for body measurements. However, relying solely on the checkerboard grid may not be ideal in all conditions. For example, in low light or other challenging environments, identifying the grid's edges might become difficult. To overcome this, the system integrates a matrix of dots into the grid. These dots serve as additional anchor points, enhancing stability and reliability. The software looks for these dots in real time, mapping them against pre-programmed anchor points in the system's database. This combined approach of checkerboard grids and dot matrices provides a dense set of reference points, enabling the software to precisely map the body's outline, even under less than ideal conditions. Once the system identifies the anchor points, it calculates key measurements such as hip circumference, thigh circumference, leg height, overall body height and width. The use of anchor points and predefined calibration reduces reliance on high-resolution image data, making the process faster, more efficient, and less intrusive. The system is designed for simplicity and convenience. Users only need to set up the backdrop once and capture images from multiple angles, front, back, and both sides. This single setup allows the software to create a comprehensive model of the user's body. The backdrop is reusable, meaning users can take updated measurements if their body changes over time, e.g., due to weight fluctuations. The system also incorporates a membership-based business model to build customer loyalty and ensure long-term engagement. Members receive access to services such as tailoring updates based on their new measurements. For example, if a customer gains or loses weight, they can send in their clothes for adjustments based on updated body data. This not only creates a more personalized experience but also helps the business manage costs by controlling the distribution of backdrops. Instead of handing out backdrops indiscriminately, the membership structure ensures they are allocated efficiently and sustainably. This approach provides a scalable, user-friendly system that prioritizes privacy, convenience, and precision. By addressing key concerns such as body image discomfort and data security, while also leveraging advanced technical methods like dot mapping and matrix modeling, the system offers a unique solution for modern consumers. Its adaptability and reuse potential ensure that users can continue to engage with the platform as their needs evolve, building a strong and loyal customer base. To reverse engineer distortions caused by characteristic camera properties, we use a grid-based, pixel-mapped representation of imagery. This grid provides a structured way to measure and correct distortions. Ensuring precision in this setup requires consistency in the size of the dots and the checkerboard grid used for calibration. These elements must align perfectly with the software data, necessitating careful attention to how the grid is designed and printed onto the backdrop. The backdrop's design and material must meet strict precision requirements. The chosen material should reflect the data in the software accurately and consistently. For this reason, the dimensions, tension, and material properties of the backdrop are critical. The backdrop must also balance precision with environmental responsibility. Utilizing biodegradable and natural fabrics aligns with sustainability goals, a core aspect of our business model. One prototype for the backdrop is muslin cloth, which is lightweight, cost-effective, and widely available. Muslin's flexibility makes it suitable for producing large grids, and it is easy to roll up for storage and transport. However, to ensure stability, the backdrop requires a backing that accounts for its dimensions and tension. The backing must allow for easy rolling and unrolling without causing creasing or misalignment, and it must be simple for users to assemble. Cord has been proposed as a prototype material for the backing due to its affordability, biodegradability, and structural support. This design ensures that, when rolled, the edges of each panel align with predefined creases, facilitating compact storage. When unrolled, the backdrop will feature hooks or attachment points to secure it to a self-standing frame. This frame provides the necessary tension to keep the backdrop completely straight and prevents flapping or misalignment. Although some assembly is required, the process is straightforward, ensuring convenience for the customer. Maintaining high precision in the backdrop's construction is essential for accurate distortion calculations. Each backdrop may have unique variations, even if mass-produced, making it necessary to track these differences. Assigning a unique serial number to each backdrop allows for precise calibration tailored to that specific unit. This serial number links to a database that stores the backdrop's unique variables, which are factored into real-time distortion correction algorithms. This approach requires additional storage and data management, emphasizing the importance of a well-structured database. Implementing a membership system ensures better organization and reduces the risk of chaotic, unstructured usage patterns. Membership simplifies database management and fosters a streamlined user experience. The current prototype for the dot matrix features a spacing of 0.25 centimeters between dots. Determining the optimal dot size and spacing requires physical prototyping and testing, as these factors directly impact calibration accuracy. While this prototype serves as a starting point, further modeling and experimentation will refine the design. Distortion often occurs most prominently at the periphery of an image due to parabolic warping. Addressing this requires a nuanced understanding of parabolic distortion. The parabolic shape naturally focuses light and distortion toward a focal point. By aligning dots within this focal region, the system can recalibrate the rest of the image more reliably. Strategically placed dots within the matrix correspond to geometric points influenced by the parabola. This allows for precise mapping of distortion to the areas experiencing the most error. Software algorithms use these reference points to calculate how the rest of the image should be adjusted. Dots closer to the focal area enable the detection and correction of smaller distortions, significantly improving overall accuracy. The user experience is designed to be simple and intuitive. Users align themselves in front of the dot matrix grid, and the software automatically handles calibration. Guided by visual prompts, users are directed to stand in the correct position relative to the grid and focal points, ensuring accurate measurements. This approach minimizes the need for technical knowledge, making the system accessible to non-experts. The system leverages parametric modeling and geometric principles to achieve precision. Unlike AI models that rely on extensive training data and computational resources, this system uses deterministic mathematical models based on known relationships. These models translate physical distortions into mathematical corrections without requiring large datasets or complex AI training. By layering different principles, such as checkerboard grids for spatial alignment and parabolic distortion correction, the system addresses various sources of error. Each layer focuses on a specific aspect, creating a robust, multifaceted framework that reduces measurement inaccuracies. The system relies on established geometric methods, such as camera calibration, distortion correction, and inverse mapping, implemented using straightforward algorithms. This reduces dependence on AI, which often requires significant data, training, and computational power. Once coded, the mathematical models perform real-time corrections on consumer devices with minimal overhead. Because the system is rooted in geometric principles, it is easily adaptable to various devices, including smartphones, webcams, and laptops. The focus on focal points and distortion models ensures flexibility across different camera configurations. With minimal adjustments, the system can accommodate a wide range of consumer devices, making it a versatile solution for precise body measurements. While mathematical models are often seen as predictive, this system is reactive. It dynamically adjusts based on the configuration and input data, making it a flexible and responsive solution. The algorithm reacts to distortions and corrects them in real time, ensuring consistent performance across diverse scenarios. Users can calibrate their devices using a checkerboard matrix and dot placement. The system adjusts automatically when users follow the straightforward setup process. Once calibrated, the system will continue to function effectively, even if device or camera settings change. A related concept we discussed in a previous video on this channel is the Jacobian matrix, a crucial mathematical tool in geometric transformations and distortion correction. In simple terms, the Jacobian matrix represents the partial derivatives of vector-valued functions, which describe how small changes in one set of variables, such as image coordinates, translate into changes in another set of variables, like real-world coordinates. For example, in the context of image correction, the Jacobian matrix helps us understand how the observed distortions in an image relate to the actual physical dimensions or positions of objects in the real world. The key idea here is that when analyzing an image, any distortion or change in the appearance of the image due to factors like lens distortion or perspective shifts can be captured mathematically. The system interprets these changes through the partial derivatives, which represent the rate at which these distortions occur. This information is used in the software's algorithm to correct the distortions and make the image conform to its intended representation. In the case of the body measurement prototype, the grid of dots on the checkerboard serves as reference points. These reference points allow the software to measure local transformations, such as those caused by lens distortion or perspective shifts. Each dot in the grid becomes a computational node, and the relationships between these dots define the transformations happening in the image. The position and spacing of the dots are crucial because they provide localized data on how the camera distorts the image. By analyzing the displacement of each dot relative to its ideal, undistorted position, the system can compute the local derivatives of the distortion function, which are akin to the elements of the Jacobian matrix. The advantage of using a grid of dots as reference points is that it allows for a detailed, localized analysis of distortion. Instead of relying on a broad, uniform correction approach, this method adapts to the specific distortions introduced by the lens and camera settings. The more tightly packed the dots, the more data points are available for the system to calculate local derivatives and refine the correction model. This approach ensures that even subtle distortions are captured, which is particularly important when the system is required to correct images with high precision.